So an exponential relations, we've talked about exponentials. We talked about when we're talking about exponentials, what's special about exponentials? The equation, what's special about it? The exponent is a variable, right? It's a letter, right? In the other cases, the exponent was a number. In this case, your exponent is a variable. So the general exponential relation, it is y equals, I'm gonna write this because this is the one I showed you yesterday, and this is basically the basic exponential equation. Then we'll go to the little bit more complicated exponential equation, the one that starts with an initial value. So in this case, my initial value is 1, okay? Because my coefficient, can you just look up here and then you can copy this in a second? So you see the exponential here is here is 1. That's not always the case. It's not always that I'm gonna start with an initial value of 1. A lot of times, like when they do science studies or when they do, let's say they're studying a certain type of element in the ground, they're not gonna start with 1. They're gonna start with a certain amount. We call that the initial value, okay? And usually we say that the initial value has a letter of a, b to the power of x. So this is the step up to this equation, okay? Where my initial value right here is not 1. We'll talk about this and we'll do some examples where the initial value is not equal to 1 later on. Okay, now yesterday we talked about the base, b. So what did the base represent when we were talking about the table of value? What was the base? What did it represent? The whatever you multiply by, and we called it what?
Ratio.
The ratio. That's right. So where the base, where b represents the common ratio. So in yesterday's example, it was, the first example was 2 because we were doubling, and the other examples it was 3 and a half, right? So it's your common ratio. Now we have two types of exponential equations. We either have a growing exponentially or we have a decreasing exponentially, okay? So we call them exponential growth and exponential decay. Okay? As you can see, the exponential growth, it starts with a flat horizontal line and then it grows fast exponentially. So as x increases, as x is increasing, my y is increasing as well. On the other hand, when you have an exponential decay, you're going to start high up, and then as x is increasing, your y value is decreasing until it becomes horizontal. Okay, so growth, the first one, the second one is decay. Now, what makes them growth or decay is the base. That common ratio is what makes them an exponential growth or an exponential decay. If the base is greater than 1, so any value greater than 1, then you're going to have an exponential growth. If the base is between 0 and 1, okay, so 0.5, 0.25, 0.35, 0.75, 1 over 2, 1 over 6, any value between 0 and 1, then we're going to have an exponential decay. Do you understand the difference between the two? If it's just 1, then you will have a, no matter, it will never be 1, because if it's 1 power of 1, what's 1 to the power of 2? 1. 1 to the power of 3, 1. 1 to the power of 4 is 1. So whenever you have, if your base is 1, you're going to have a horizontal line. So that's why the base is never equal to 1. Okay? It's either between 0 and 1, or it's greater than 1. So when b is greater, then the relation is, it's growing. It's a growth, right? Because as you see, the graph moves up to the right. As x is increasing, y is increasing. When the base is between 0 and 1, then we have a decay. Then the relation is decay, which means it's, the graph moves down to the right, which means as x is increasing, the y value is decreasing. So we call that value of b, we call it either the growth factor or the decay factor. Okay? So that value right here, so in this case it's 2. It's called the growth factor of 2. And then this one is called the decay factor of 0.5. Okay? So this is the technical name for it, decay factor or growth factor. So when the question is asking you what's the growth factor, you're going to have to look at your base and you're going to have to state it. What's the decay factor? You're going to have to look at your base and you're going to state it. Now, what we're doing right now, we're looking at the different characteristics of the two. Okay, we're looking at the characteristics of these exponential functions. So if I want to find the x-intercept, what do I have to do? That's y equals 0. Okay? Because remember, if you're looking at an x-intercept, right? This is the x-intercept right here. Right? The y value is 0 at this point. Correct? So anytime you're looking for an x-intercept, you're going to have to set y equal to 0. So let's do that. Let's set y equal to 0. And let's try to solve. So I'm going to use the first example. What values of x do you think you're going to plug in to get a 0? Guess. Take a guess.
0.
So if you plug in 2 to the power of 0, what do you get? 1. Give me other values. It's okay to guess wrong. Guess. 2 to the power of 5. Do it on the calculator. Tell me what you get. Do 2 to the power of 0.5. What do you get?
1.
Okay, so it doesn't work. Give me something else other than 0.5 and 0. 2 to the power of 1. What do you get? We're just guessing. We're just plugging values in for x. Hopefully we can find a value where my y is 0. We're just doing guess and check.
Is it -1?
Try it. 2 to the power of -1. What do you get? What do you get? 0.5? Okay. Try 2 to the power of -10. What do you get? 0.0 what?
0.0009.
Okay, so there's a 9 at the end, right? Okay, so it's not 0 yet, right? Plug 2 to the power of -15.
0.3.
Times 10 to the power of -15.
15. 2. Oh, 2.
Yeah.
15.
So it's 0.00003. Okay. So even if you plug a very big negative number, you're gonna get 0 point something 0.0000 and a number. You're never gonna get 0. Okay? So there's no x value that I can plug in that gives me a y value of 0. It's gonna approach the 0, it's gonna get close to it, but it's never gonna be 0. Maybe the calculator will not be able, maybe if you plug in 2 to the power of -1000, the calculator will give you a 0 because it will think it's 0. But it will never touch. Okay? So what's gonna happen is this. What happens is, as you go toward the negative x values, your graph is going to get close to your x axis, but it's never going to touch that x axis. Even if you when you magnify it, right? When you put, like when you actually zoom in, you're going to see that it's never going to touch. Okay? So when we have a regular exponential function like this, y to the power equals 2 to the power of x, or 7 to the power of x, or 100 to the power of x, we're never going to have x intercept. Okay? Same with the decaying one. So what in the other hand, the decaying one is going to be like this, where it's going to go like, as you go, as x increases, then it's going to get close to this. Okay? So in the case of exponential, unless I have transformation, which we're not going to talk about in this course, right? Transformation, remember transformation from quadratic, where you have horizontal and vertical translation? You guys remember that? Yeah? Unless I actually have a translation where I take this graph and then bring it down, that's the only time that you're going to start seeing x-intercepts. Okay? But in the basic ones that we're going to do in this course, we're not going to have x-intercepts. Okay? It's going to get close to that x-intercept, but it's never going to reach it. So if you try, let's say, 2 to the power of -10, it's going to be a tiny number, but not 0. Now, if I want to look for the y-intercept, what do I have to do? What do I plug in for x? 0. If I'm looking for the y-intercept, so I'm looking for this, right? I'm looking for this value. The x value right here is 0. Okay? So I plug in x equal to 0. Now let's do that. If I have y equals 2 to the power of x, and I do 2 to the power of 0, what do you get? What's 2 to the power of 0? 1. How about if I take the second one? Y equals 0.5 to the power of x. What's 0.5 to the power of 0? 1. Okay? Remember that no matter what the base is, if you take it to the exponent of 0, you're going to get 1. Okay? So my y-intercept is 1. I'm going to take you back to the graph right here. And then we're going to locate the y-intercept. So this is the y-intercept here. Right? And it's equal to 1. And this is the y-intercept right here. And it's equal to 1. Okay? And then you see that the graph is extending. It's never touching that x-axis. If you actually zoom in, you won't see it touching.
So is it always going to be like that until we go into transformation?
Until we do transformation, or until we have an initial value. Once we have an initial value, then your y-intercept is going to change. Right?
Can I see the bottom?
Yes, of course. Okay? Unless I have a different initial value. So the minute that I have, let's say I'm starting with 100, okay? Let's say my equation is this. 100 times 2 to the power of x. That's still exponential, correct? That's exponential. What's your base? What's your base? 2. 2. Your base is 2, right? So it's double. This is your initial value, right? Now if I plug in 0 for x, what's 2 to the power of 0? 1 times 100? 100. So my initial value is 100 in this case. You see? So now the graph for this is going to be starting at 100, and it's going to look like this. Okay? But we'll see examples like this. You don't have to worry about it right now. You guys okay with this? so far? Okay. So far all what I did is I looked at the two different graphs, the exponential growth and the exponential decay, and I looked at different characteristics of each. So we have a table of values, and they're asking us to use a table of values to answer the questions we need. So the table of values is asking you to find the ratio. So what do you have to do to find the ratio?
What?
Divide what by what? The second by the first. So remember, I have to divide 3 by 1. What do you have? 9 divided by 3. 27 divided by 3. By 9, sorry. 81 divided by 27. Is the relation exponential?
Yeah.
And how do you know that?
Same ratio.
That's right. The ratio is constant, right? So it's the same exact value for my ratio. So yes, the relation is exponential because the ratio is constant. Can you guys define the word initial value for me? What does the word initial value mean? Your starting value at, what would the x value be then? 0. Okay? So if they're going to ask you for your initial value, you're going to have to go and look for, when x is 0, what's my initial value? Okay? So in this case, what's your initial value? 1. Now, state the equation of the relation. So we have to actually write the equation. It's not given to us, we have to write it. Okay? So remember that I told you it should be y equals ab to the power of x, where the initial value is a. Right? But what did we say our initial value is? 1. Because the initial value is right here, right, at x equals 0. So that's your initial. So in this case, my initial is 1, which is good. So my initial is 1. What do I replace b with? 3. Because remember, b is your ratio. And then to the power of x. So basically your equation is y equals, I don't have to keep that 1. It doesn't have to be there. It's 3 to the power of x. Are you guys okay with that part? That's right. So if the initial value, let's say if that value right here was 0, 2, right? That a value is 2, then it will be 2 bracket 3 to the power of x. 2, it will be 2 bracket 3 to the power of x. You can't multiply the 2 and the 3. It's not allowed. Okay? Because remember, BEDMAS tells you what? Brackets exponents, right? So you have to do the exponent first, then you multiply. What's wrong? Are you guys okay with this? But in this case, my initial value is 1, so I don't have to worry about this, right? Now they're asking us to graph the relation. So just take your original point and graph. I already have a table of values, right? So I can go 0, 1, 1, 3. Find my points and then join. much do you think I should go up by? If I go up by 3, would I be able to fit a lot? Let's see. 3, 6, 9, 12, 15, 18. I won't be able to fit a lot of these points. So maybe I want to go up by 10. Yes, my points are not going to be very clear, but I can fit some of these points, okay? So if I go up by 10. So it was 0, 1. So what I'm going to do is I'm going to estimate. Again, this is not going to be exact value, right? 1, 3. 2 was 9, right?
Yep.
And 3 was 27.
Yep.
And 4, 81. Is that right?
Yep.
Okay. 5 was what? Oh, we don't have 5. Okay. So I don't have to worry about this. So you see that's an exponential growth. And we know that because the base is greater than 1. You guys good with this? Can I go to the next page? So a small garden center propagates tulip bulbs. The gardener begins with 100 bulbs. Each bulb produces several new bulbs. So each one produces several ones. 3 of these are kept to the next round. So each bulb produces, let's say, 5 or 10 or whatever, but they only take 3 from each bulb to regenerate. Okay? Do you guys understand that? So basically, if I have 100 bulbs to start with, I'm just not going to draw 100, but let's say this is my first 100. What's going to happen? How much I'm going to take from each one of these?
3.
3. So in the next round, how many new bulbs I'm going to have? How many new ones I'm going to have? 300 in the next one. Right? Yeah? And then in the one after that, each one of these is going to produce 3. So how many would I have? 900. You see what the question is telling you? Okay? So let's reread the question. So a small garden center propagates tulip bulbs. The gardener begins with 100 bulbs. Each bulb produces several new bulbs. 3 of these are kept for the next round. Write an equation to represent the number of new bulbs. What's my initial value here? What am I starting with? How many bulbs?
100. Oh, 100.
100. So my initial value is 100 bulbs. Okay? Now what's my growth factor? How much am my numbers gonna be growing by? It's going to be tripling, right? So it's going to be multiplied by 3. right? Because each one is going to produce 3. So multiply by the growth factor for each round. Okay, so let's start. Number of bulbs is 100 for my first round. This is what I'm starting with. Then for my first round, I'm going to have 300 because each one is going to be producing 3 times 100, which is 300. Now I'm going to have to multiply this by 3 again, right? Because my next round, I'm going to have produce 3 more for each. Do you guys understand that? So I'm going to take this, and I'm going to multiply it by 3. So this is my second round. Okay? Then we're going to take the second round and we're going to multiply it by 3. And that's going to be what? 2,700? 2,700, right? Now I'm going to, what do you see? What do you see here? Do you see any pattern? What is it?
You just add an extra 3 to every one.
You add an extra 3, you multiply an extra 3 for every single one, right? So how many 3s did I have for my first round? 1 3. How many 3s did I have for my second round? How many 3s did I have my third round? If I want to write 3 times 3 in order in exponential, how would I write it?
3 times
3 to the power of what?
3.
3 to the power of 2.
Sure.
Right? How would I write 3 times 3 times 3 in exponential? Okay. Now if I have n terms, n rounds, what would it be? 3 to the power of n. Right? It could be 10, it could be 50, it could be 500. Right? It's 3 to the power of that number, whatever that number is. Right? Now remember that it's always multiplied by, what do we call this value, the 100? What is it? Initial value. Okay? So it's always multiplied by your initial value, which is the 100. Okay? So that means my equation is 100, my initial value, times 3 to the power of n. Okay? Remember we already explained this in the previous question, but what was my initial value? The previous one. What was the initial value? 1. In this case, my initial value is 100. Okay? My ratio is 3. My growing factor, my growth factor is 3. And then it's exponential. Okay? So I already introduced to you this formula, which is y equals a b to the power of x, where a is the initial value, b is the decay or growth factor, and y is how much you have left after x period of time. How much do you have? So the equation for this question is y equals 100, 3 to the power of x. Let's look at this together. have a group of bacteria that doubles every hour. If you initially start with 120 bacteria, I'm going to write an equation that represents this scenario. What would your equation be?
Y equals 120 brackets 2x.
2 to the power of x. That's right. 120 is your initial, so that's your A value. It doubles, so that means your B is 2, because doubles means 2, right? And then to the power of x. Good. Who doesn't agree with this? Or doesn't understand it? Now, my question to you is, how many bacteria would you have in 10 hours? What do you do? Plug in 10 for x. And then you have to do 2 to the power of 10, and then what? Multiply by what? By 120. So find how many bacteria would you have after 10 hours. One,
Oh,
two,
wait, sorry.
go baby.
122,880.
So this?
Yeah.
So after 10 hours, I have 100, I started with 120, right? 10 hours later, because they're doubling every hour, I'm gonna end up with 122,880 bacteria. Are you guys okay with this? Okay. Now, in this case, they are giving us the growth factor or the decay factor. So the growth factor is doubling. So I know that my base is 2. Okay? There are some cases where they don't give you the growth factor, but they give you a growth rate. There is a difference between the two. A rate is percentage. A factor is not a percentage. Okay? So, attention, full attention on me. So, there's going to be 2 different types of questions. Question that would give you the growth factor, which is double or triple, right? Or even it tells you that it's half, so it's 1.5, it's 1 over 2, right? Then that's easy, they already gave you B. So in this case, B is equal to 2, or B equal to 3, or B equals to a half, right? But other times, they're gonna give you a growth rate. There's a big difference between these two. Growth or decay rate. A rate is a percentage. Okay? So let's talk about, for example, bank accounts. Okay? So let's say you go to the bank and you put $1,000 money in your bank account, and the bank is going to give you 2% or 3%, let's say, of interest. 3% interest on that $1,000. That 3% is called the growth rate. Okay? So you can't use the 3 as your base, because then it's tripling, and that's not the case. Your money is not going to triple, trust me. Okay? It's only going to grow by 0.03%, 3. And if you actually plug in 0.03, what's going to happen is your money is going to even go lower. Right? So if you multiply 1,000 by 0.03, you're going to get what? $30?
Yeah.
Right. And then now you have an account $30? Doesn't make sense. Okay? So in this case, we have a little, like a formula that's a little bit different. So we have two formulas actually. We have one for the growth and one for the decay. Okay? So the one with the growth looks like this. You've seen this before? And the one with the decay looks exactly the same, but with one little difference, and that is minus r. So in this case, it depends if you're collecting interest or if you're losing value. Okay, so let's say if you buy a car and then you bought the car for $10,000 and then it's losing some of its percentage, some of its value over the year. So that would be a decay in this case. So the difference between the two, eyes on the board for a second, the difference between this and what we're used to, with this, is that your base is not given to you. You have to find it by doing 1 plus the rate or 1 minus the rate. Okay? And that would become your base. Okay? Always remember that the rate has to be in decimal, it can be in percentage. So if the bank gives you 3%, you actually have to plug in 0.03 for R. Okay? Or if you're losing, let's say, out of your car value, you're losing 15% every year, that's going to be 0.15. Okay, so you have to change the percentage into decimal by dividing by 100. Do you guys understand that? Let's look at a question, and then I can give you another example that you guys can work on. So, suppose you have $500 in the bank, and you deposit it into a savings account that pays 2% interest per year. Find the equation that models this exponential growth. So, y equals, now that's a growth. It's telling you it's exponential growth. So which formula do I use?
So it'd be 500 bracket 1 plus 0.02. When it says year, would it be 12?
Now per year, we don't know how many years, so we're gonna put it to the power of n. Okay? Because we don't actually know how many years it's been in the account for. Okay? But you know that n is the number of years. So let's say if I ask you in this next question, find the amount of money you will have after 3 years, then what are you gonna plug in for n? 3
years.
That's the number of years. So that's 3 years from now, right?
Yeah.
So in order to find out your amount, you're gonna say y equals 500, 1.02.
So would that be 36?
To the power, no,
Oh,
it's
okay.
in years, right? It's not in months.
Oh, years. Yeah,
it's in months, in years.
Three.
Yeah. So what do you get when you do that? What's the answer? 530.61? 60.1? 61? Okay, 604, so that's 60. So that means after 3 years, you're gonna have in the account, you're gonna have $530.60. Are we okay with this? So here's a scenario for you. You guys listening? You bought a car for $15,000. the car value will depreciate by 8% every year. Find an equation that models this situation.
You just want.
So you bought a car for $15,000, and the car value will depreciate by 8% every year.
So you want the equation?
I want the equation.
So it'll be A bracket 1 minus R bracket n.
Okay?
Exponent.
Yeah, and now fill in the actual values for A and R. Yeah.
1500 bracket 1 minus 0.08 bracket n.
Yeah, it's 15,000.
Oh, of course.
Okay, that's right. So the equation so it will be y equals 15,000, 1 minus 0.08 to the power of n. Good. Now, what would the value of the car be after 5 years? Let's say 5 years.
Yeah. Is it 9,000?
I don't have a calculator. How about you guys? You tell me.
9,886.
9,886.
I got 9,005.
Did you put it exactly the way it looks like that in the calculator?
Pretty sure.
Okay, I'll come and check.
Which one? You got 9,000?
9,886. Where do you get the 0.6 from?
Oh, I did this.
Was it exactly 0.6?
Yeah.
Did you do it to the power of 5?
Well, oh no, I think it's time. I times it.
So 1 minus 0.08 to the power, should be to the power.
Times it.
Power of, it's not times, right? Power and times are not the same. Times. Okay, so enter it exactly the way it looks in your calculator, and your calculator should be used. So it's 9,886.22.
Okay.
After 5 years, this is how much your car will be. Okay?